Good morning, everybody.
Good morning.
Hey, let's see here. So, today I think we're going to talk about a little bit about FTIR sampling, and then a little bit about Raman, and I think that should probably do us for the day. You'll probably recall that last time we just talked about infrared and like general aspects of what makes a molecule vibrate and what imparts the frequency and the intensity to an infrared absorption band. And the frequency is the frequency of an infrared band is basically given by the mass of the constituent atoms and the bond strength. It's actually the square root of that ratio, the square root of K over mu. K is the bond strength, and mu is the restoring force for the bond. So, for example, if you have a COH and then a COCl, for example, the CCl bond will have a much lower frequency than the CO bond. They're similar sort of single bonds to a heavy-ish atom, right? And of course, we're talking about group frequencies here, which are not exact because they are characteristic of just like two or say up to four oscillating masses, but they're good enough. So, and the intensity of an infrared absorption is, hold on, I'm getting tons of text here. Okay. The intensity of the band is proportional to the magnitude of the changing dipole moment. So like, and it's kind of beautifully simple like that. If you have a diatomic, like say, CO or like carbon monoxide or something. Actually, that's a crappy example. Like CN, like cyanide, HCN, for example, it has a very large dipole moment, and it will have a large infrared absorption. But a molecule of very small dipole, like CO, for example, will have a smaller dynamic dipole, and it will have a smaller transition dipole moment, smaller absorption coefficient. Now, there's just a short topic here on infrared spectroscopy and the applications of it, right? So basically, as everybody here knows, I think, is that infrared spectroscopy is a little bit tricky because optics and solvents have strong absorption, and the infrared beam is invisible, so they're hard to align. The sources are weak because there are no continuum sources, no broadband sources of infrared that are known except for black bodies. And black bodies have some fundamental limits to the intensity of radiation that they can produce. So that being said, they're a little bit weak. And then the detectors, some detectors are a little bit insensitive, others are decent. So the strategies that we use to make IR spectroscopy work are use interferometers instead of monochrometers. Interferometers are those light mixing devices that turn light frequency into audio frequency by moving a mirror. So high light frequencies come out at high audio frequencies, and low light frequencies come out at sort of low audio frequencies. And then you just sort out all of the different components using using a Fourier transform that takes all of the light that's all smashed together and sorts it by wavelength. Right? And obviously, since silica optics absorb infrared, you can a lot of what's done is using mirrors. You can use a aluminum or gold for surface mirror, and they're very nice. Where you need to do transmission, for example, through a beam splitter, you can use high atomic mass materials. Hey, Tyler. And you can, and so these are materials like calcium fluoride, zinc selenide, and ACL. There we go. And we can also use solvents that are transparent within a certain selected spectral band. And this is it's a valid strategy, but it's sort of limited. You can also avoid solvents completely, and you can use reflection absorption instead of transmission. So let's talk about some examples of these approaches, right? Starting with the worst one, I think, is to use a solvent for the IR spectrum, right? And here's 8 examples of solvents that you can use. And there are horizontal lines where these are solvents are transparent in the infrared, and you can make a solution of them, and you can get a spectrum, for example, of tetrachloroethylene in the, into this region, 1200 to 5000 range, and etc. This is not very common, but I'm sure it works. I have never done it personally. Another way to do it is to use infrared transparent plates, and sodium chloride is a very common choice here. And basically, what you do is you just you can take your neat solvent. You can take a neat solvent, for example. Let's say you've got a liquid organic product and you want to measure it, and you just plop it into the sandwich between 2 plates and smash the plates together, right? And typically you'll get like a 10 micron thick sandwich that way. I mean, it's not exact by any stretch. It could be 0 or it could be 30 or 50 or something, but you can adjust it a little bit by squeezing the sandwich or adding more stuff, right? But this reduces the path length really dramatically, right? And so now a neat sample has a concentration. It has a number of moles of solute per liter of solvent, right? So for example, water is 18 grams per mole and 1 gram per cubic centimeter. So that happens to be 55 moles per liter. So let me show you how you do that calculation just real quick. Switch over here.
Oops, what happened? Oh, here.
Oh, hold on.
Oops, sorry. Hi.
Hey, hi, Connie.
Every time I join, this always unmutes me, so I'm sorry.
That's okay. I'm just trying to find my pen here. Here it is. So let me get this share up here. So can you guys still see the notes?
Yeah.
Thank you, thank you. So that must be the wrong. There we go. So for example, when we're referring to the molarity of a neat solution, right? We can say, well, this is a number of moles divided by number of liters, right? And so the number of moles is given by the grams over the formula weight, right? So to get formula weight or to get moles in the numerator here, we're going to have 1 over formula weight. Oops. Have 1 over formula weight. One over formula weight in grams per mole. And then we're going to multiply that by moles per cubic centimeter. It's going to be grams per cubic centimeter, right? And so the grams are going to cancel here. That's going to be moles per cubic centimeter. And now we're going to multiply that by 1,000 cubic centimeters per liter, and this equals moles per liter. So, for example, for water, we have 1 mole over 18 grams, right? That's 1 over FW, times 1 gram per centimeter cubed times 1,000, and this equals 55 moles per liter. So that's an intrinsic property of any liquid material, or actually any solid material for that matter. And so if you know, so for example, if you have a neat solution and a 10 micron sample gives an absorbance of 0.1, then you can put in these values. So the absorbance of 0.1 is here. The molarity is in the denominator here. Actually, I should probably have some parentheses around it there. There's the 10 molar, and there's the 10 microns. And that comes out to an epsilon value of about 10 per molar per centimeter. And so, okay, well, that's fine. That's a 10 micron thick sample. That gives an absorbance of 0.1. Well, why don't we just use a normal 1 centimeter path? What type of absorbance would that give? Well, we can plug things back in here and say, well, there's 10 times 1 times 10, right? That's 10 per molar per centimeter times 1 centimeter times 10 moles per liter, right? And that gives us a unitless absorbance of 100. And the transmittance through that would be 10 to the minus 100, or a number I can't even write. So that's why you absolutely need a thin path, a small path length to get these. It's an interesting sort of a limitation to the absorbance method in general. You need light, but you can't have too much or you can't have too little. So it just sort of brings us back around to a theme that we touched upon in optical spectroscopy in general. So now, another way you can handle a solid, for example, is you can put that solid into a pellet, right? In that case, you're going to mix your analyte with some, typically some potassium bromide. That's some crystals, some salt, right? And then you grind it up, and you make a good homogeneous solid solution.
Wait, Professor, can you go back up?
Sure. Hold on just a second.
Just up to where you wrote about like the 55 moles per liter or something, like probably up there. Yeah, they're right there, right there, right there. Okay, so what is that? Okay, so at the part where it says 1 molar over 18 liters times 18 divided by, it looks like CW. I'm not sure what that says.
Oh, I'm sorry. That's centimeters.
Oh, centimeters. Okay, thank you.
Yeah, yeah. It's actually supposed to be cubic centimeters there.
Oh, okay, thank you.
Yeah, so this is rho, and this is the reciprocal of the formula weight. So the concentration here, we'll call it the concentration is equal to rho over formula weight times 1,000.
Okay, thank you.
Okay, you're welcome. So now let's see here. So yeah, so you can make a solid solution here, right? And then basically what you do is you take this solid solution, which is basically just ground up stuff together, and you use KBr because KBr has KBr undergoes cold flow. So it's cool, right? Because if you put KBr crystals under a lot of pressure, they will flow. Cold flows. So it's also nice and infrared transparent. Right? And who can tell me why KBr is IR transparent? Oops. Let's see. Let's pick on Gavin. Nah. Okay. Why is KBr infrared transparent? Because what are the two things I mentioned earlier at the beginning? Two things that make that determine the intensity of an IR band. There's the effective mass and the uh, bond strength, right? So let's see here. Effective mass mu is equal to m1 m2 over m1 plus m2. That's very high. So potassium's heavy and bromine is heavy. They're actually almost equal mass. So and KBr is probably around 30 for effective mass. And also the bond is relatively weak. It's not covalent. So the frequency is proportional to the square root of K over mu. So because K is relatively small and mu is relatively large, then the KVR stretching frequencies are way into the far infrared. Right? So in any case, and it also cold flows, so you can mix your solid. You just use a few milligrams and make a millimeter or so. Take a few milligrams of sample, mix it up with KBR, and this is done in a mortar and pestle. You know, if you want to feel like an old timey chemist, you can grab a mortar and pestle and go add some KBR and some organic material, and then you make a few millimeters, maybe 1 to 3 millimeter thick, a pellet in a die. And the die usually has vacuum. You pull a vacuum and you push at the same time. And this makes an approximately transparent. I mean, it's not like super clear like glass, but you can sort of see through it. Call it translucent. Little puck. And then you can put that into the infrared spectrometer, and that'll get you into the sweet spot for absorbance in most cases. So let's just take a quick thought about this. And if the absorbance is too low, and you have more material, what can you do? Matthew?
Yeah.
You're always listening. Thank you. If the absorbance of the puck that you make is too low, what can you do?
I'm guessing that you could probably dope it.
Yeah, basically you just add you make a new puck with more stuff, right? And if the absorbance is too high, you make a new puck with less stuff. I mean, it's a sort of a stupid question, I know. I'm just sort of like trading, trading thoughts, So re-prepare with less or more,
What's the margin of error?
The margin of error is between about 0.1 to 2. So there's a factor of 20 or so in concentration that you can span to get a given peak on scale.
Okay, so you don't have to be super duper precise.
No. You don't have to. Just so long as you can measure it well, And depending on the instrument, you can sometimes get a very good puck or very good absorbance rather that might have an absorbance of 0.005 or something, or it could be as high as maybe 2.5 or something if you've got a really strong source. But anyway, it's just a sampling method. It's worth a mention. It's worth talking about a little bit here. All right. So next thing you can do is you can also mull, right? And this is basically just making a solution, right? And mulling is kind of weird because if you have a Daniel here, hey Daniel, when you have a solid that may or may not really be soluble in mineral oil, which is just an aliphatic oil, could be octadecane or hexadecane or something, or you could use fluorocarbon oil, which is it's probably fluorinated octane, fluorinated decane, something like that. And these are organic molecules themselves. They have predictable spectra, right? So you can say, oh no, okay, I'm using Ujol, so I can't use the 3000 range. I can't use this, right? So it's a solvent method, but it's not that uncommon. So you can make this mull, and you can grind up your molecules into this oil, and then sandwich them in the KBR plates or NaCl plates for that matter, and get a measurement. So I won't say more about that there. I'm not really that big into these things. I'm just sort of like trying to translate some information here. So in general, you've always got this problem of measuring a blank, right? And so you can approximate a blank in many cases by just putting the puck in. Or you can make a blank puck, for example, using a press. And that's fairly common. Or you can use the windows that you're measuring with, and you can put the mulling oil on the windows, and that'll make a decent blank. But these are all sort of semi-quantitative methods, because there are reflection losses and other things that you can't exactly match using these funky infrared sampling methods. So these are actually, they're qualitative, or if you're good at them, maybe they're semi-quantitative. So we could write semi-quantitative. And however, this information is still very useful. And you can identify functional groups, and you can spectral fingerprint, right? So you can say, well, I know this molecule has OH and a carbonyl and an amide, and maybe a double bond in there, and you can or an aromatic group or something, and you can also you can identify the functional groups, or you can just fingerprint, use the near infrared or the the mid infrared region, and you can say, okay, well, molecule A looks like this, molecule B looks like this, molecule C looks like this. Mine looks like molecule B, and so you can get an identity without actually going into what specific functional groups make up the molecule, right? And that's one way of quantifying this. And I can recall an interesting case where a friend of mine was doing some solid phase synthesis. So he had these beads, and they were some sort of plastic, right? And he was adding step by step. He was adding functionalities to these beads, right? So he would add a monomer and then do some chemistry, and add another monomer, do some chemistry. He's building up these oligomeric these oligomers, these short polymers on beads, right? And he every once in a while he would take out some of the beads and set them aside, and then at the end he went to an infrared spectrometer and he took a spectrum of the beads at each step of the process, right? And originally there was a little bit of a mess, right? Because the beads are plastic. Oh my God, it's like huge numbers of broad absorption bands, et cetera, right? And so the spectra were congested, right? But he found, I think there was a nitrile group on the monomers that he was adding, right? So he found the spectral region where this nitrile group was added, and then he found a similar absorption band that belonged only to the plastic beads, right? And he used that plastic bead absorption band as an internal standard. And so the strength of the plastic absorption was his measurement of the path length. And then he used that, and so he divided by that band strength, right? He divided the band of the nitrile band intensity by the strength of the plastic intensity. And he was able to show at each step how he was adding one monomer at a time. If his yield was low, he would get less than one nitrile per monomer step, right? And so he was able to do semi-quantitative work like that. Does that make sense to everybody? So, Kenya, let's talk about this. Kenya. Okay. Let's see here. Okay. Let's just talk about group frequencies. Let's talk about using an internal standard. Right? We have plastic beads. And these are polyesters. And they have a PETE group. Oh, I'm sorry, that is so wrong. Oops. That's a poly weird ass molecule. Oops. Let's see here. There's a monomer from, oops, this is PETE group, right? And this has a characteristic absorption peak, right? And then the molecule that he was adding on here as a nitrile. It's a C triple bond N. C triple bond N, right? And he was adding these plastic beads to an infrared spectrometer, and he would get a congested spectrum, but he could find a peak for this guy that was resolved from the background of basically the absorbance of everything else. And then this was also resolved. There was a peak from the PETE group in the plastic, right? That was resolved, right? And so what he could do was he could take stage 1, stage 2, stage 3, etc. What he would do is he would put the plastic into a mull, and he would get an IR spectrum, right? He'd get a semi-quantitative IR spectrum, and then there would be one peak and then another peak, right? And this would be from the plastic. This would be from the nitrile, right? And then this time he'd get a peak from the plastic, and then a much bigger peak from the nitrile. Oops. And then the third one, he'd get a very small peak, and then medium-sized peak. Right? So, and what he did at each stage was he would take the plastic piece. We call this plastic 1, nitrile 1, 2, 2, and 3, 3, right? And he would integrate the peaks, right? And take the nitrile 1 divided by the plastic 1, and then he would basically integrate the peaks, right? And then this would give him a value that's proportional to the number of monomers in experiment number 1, right? And then similarly for 2 and 3, right? And so let me just see if I can get a little more real estate here. Be able to do this. So the question that I'm asking here on my horrible whiteboard is what would a plot of the number of, oops, sorry, I got that backwards. The ratio, which is the integral of oops, n1 over p1, right? N sub n over p sub n versus the cycle number. What would that look like? So you got 0, right? And so this point isn't defined, right? And then you've got 1, 2, and 3. So somebody tell me what this plot should look like. Romel, let's talk about this real quick. So there's several possibilities. Like we've got 1, 2, and 3. Got 1, 2, and 3, and we got 1, 2, and 3. Right? There's a rising, a straight, and a falling. Which of those 3 will it be? Hector? Oh my, I'm feeling lonely. Is anybody out there?
Is it B?
Yes. Leo! How are you? Yes, it's B, right? So how can it be B if the third peak is so small? How can this ratio be large even though the third peak is small?
Maybe the third peak is not really up there. It's on the second. Maybe the ratio?
Exactly. Because what happened in this third thing? If the plastic peak went down, this peak went down, right? But this is an internal standard, right? So this guy here is your internal standard, right? So it's something within the whole system that you can quantify, just you can't control how much of that gets into the beam and gets sampled by the beam, right? So you have this peak in there that you can resolve from the analyte peak, right? From the nitrile peak. And so you standardize everything to that internal standard by dividing out by that plastic peak here. Oops. Does that make sense? Somebody say yes.
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 Thank you, Matthew. Thank you. Oh, excellent. I can always rely on Matthew and hope to get me to move the fuck on. Sorry. I did not say that, did I? Oh, geez. I was just thinking this morning, I have to get reviewed. And I have to say, I have to give my referee, oh, why don't you look at, when I did it on the 28th, and now they're going to hear my bad words. So I'm sorry for using a bad word, especially to you, Catherine. But if Catherine's listening, we'll see if she reacts. Okay. So now let's talk about a little bit about the types of bands we're talking about are group bands, right? And we're picking off a part of the molecule and we're saying, well, even though each absorption band involves the entire molecule, there's something in these guys that always has a frequency close to a certain region, right? So for example, here's an ancient spectrometer trace, probably, where they have a COH containing molecule here. It's, oh God, it's this iso something or other, 1, 2, 3, 4, 5, 6. 1-methyl, 2-hydroxyl, 5-methyl pentane, pentanol rather. And basically it has this OH group on one of the methyl groups. And you can say, well, that OH group has a group frequency right around there, right? Then you make a very similar molecule here, and it has a chloro group, which shows up here, right? And there are, these are the group frequencies, right? The OH and the Cl, these are both group frequencies, right? Now, unfortunately, the Cl group shows up in what is called the fingerprint region, whereas the OH falls in the group frequency region. So that just torpedoes the idea of calling this the fingerprint region. But if you just look at the molecule, the spectra real quickly, you can see that in general, above somewhere around this cutoff, you get a piece of spectrum that's more dominated by these small group frequencies like CH, stretching and bending. And you get a region that's more dominated by complex motions that are not so easily identifiable necessarily, right? In this case, Cl, it's a heavy atom, so it shows up at low frequency here. But this really is a group. It's a group frequency because this band belongs to the CCl stretching motion. So what that means that even if it's a fairly large molecule, you know, it's this type of molecule here. The motion that gives rise to this peak is almost all localized in this CCl bond. You know? There's a large stretch here, large amplitude. Stretch for this molecule at this frequency. And all the other atoms have their motions during this mode, but their amplitude of their stretches is relatively small at this frequency. Does that make sense? Anybody? Brenda? Jesse? Min? Hector? Catherine? Vincent? Did I just put everybody to sleep?
Hector's asking you to repeat that last little bit.
Oh, thank you. Okay, cool. Excellent. I'm going to repeat it. Be nice to Hector because, let's see, I'm going to do all page. Oh, geez. I didn't have my stupid chat thingy up, so I couldn't see what people were. Okay. So, good. So, so if there is, let's say there's a, let's say you have chloroform. I'll take a decent example here. I'm going to invent some spectra here. Oh, yeah. So here's where I can write about this idea, right? The K over mu value, the root K over mu value for CCl is small, right? So this means that the frequency, or the wave number for that matter, of this group frequency, CCl, is low because it's proportional to the square root of K over mu, right? Where K is the bond strength.
Your Ks look like H's.
I know. Hold on. I'll try and fix this. Hold on. I have to, I get going fast and everything goes to hell. You know, I'm like under a little bit of pressure here because I'm like trying to keep somebody's attention. So K is equal to the bond strength. And mu is equal to the reduced mass, right? So CCl is relatively low. This makes a low frequency, low wave number. And I think what I was saying about this mode, right? It's like, let's say that if it were if this were chloroform, right? You'd have a chlorine or a carbon and a chlorine, and you'd have three hydrogens, right? And with these five atoms here, you can actually identify the mode that gives this CCl, that would give a CCl stretch at almost exactly the same frequency, right? You know, it might be slightly different, but it'll be almost the same, right? And that mode is going to be where this guy stretches out that way, and then these guys stretch out that way. This is called a symmetric stretch, right? And this is going to be new symmetric, will be around, I think that's around 900 wave numbers. No, about let's call it 820 nanometer or 820 wave numbers. Right? So because this bond here has most of the stretching motion, is centered in this one polar bond. And this is where the intensity of that group mode comes from. What I've identified a mode of vibration. And then in more complicated molecules, which have Cl, C, and then they've got three other R groups here, they will have a symmetric mode that is approximately, you know, that'll be between, let's say, 875 and, oops, sorry, I want to go, we'll call this a group mode, right? That is in the range of, let's say, 790 to 850 or so. And that means that, and even though we don't know the masses of these guys, we know that their relative motion, their motions relative to CCl are such that they stretch when the CCl mode stretches, right? And so it's the dipole moment in this bond that is giving us the, oops, that's a chemist dipole, right? So it's the dipole moment in this bond that changes, that gives this group frequency its intensity. That makes sense? try this. Hector. So it makes sense? Kenya, did that make sense to you? Oh, Kenya. No is a completely reasonable answer, or I was getting coffee is also okay. So I sort of know what's going on. Hope, did you get this?
Yeah, I think so.
Okay, all right. So, which of these bonds is stretching the most? The CCl bond here, or this, or the CR1, R2, or R3?
Is it the CCl?
Yeah, it's the CCl is it most of the stretching motion is in that one bond. And there's a small amount of kickback in the R1, R2, and R3. But it's just enough to offset the mass of the CCl bond. And the same happens in chloroform. Is the R1, R2, and R3, they're sort of more complicated.
That's just because the Cl is heavier.
Right, exactly. And Kevin says, oh, Cl, got it. Excellent. Good. Yeah. Okay, so it's just an example of like the idea of a group frequency and why it works, you know? Like these are real spectra, you know? And almost all chlorocarbons will have a stretching band that's in this region, you know? That'll be the symmetric CCl stretch. But, you know, CCl4 won't, right? Because that symmetric stretch will be much lower frequency because that will involve all four chlorine atoms, right? The K value is the same, but the mu value is much higher. But for single chlorine atoms, chlorine carbon bonds, where the other substituents are not massive, then you'll get a stretch in that region. Okay, so I kind of beat that horse to death. Now, here's an example, a really interesting example, I think, of a fingerprint spectrum. And in this case, what you have is you have this group frequency region here, and then a fingerprint region here. And you have, this is a butane, like a 2-methylbutane, and this is a 2,3-dimethylbutane, right? And the group regions are very similar, right? The same frequencies, they come right on down, you know? This has another feature here, here, but basically the overall fingerprints of these molecules are the same because they're similar classes. They're both just these aliphatic molecules, these saturated hydrocarbons. However, the fingerprint region looks very different. There's a large band here. There's 1, 2, 3, 4, 5. Here there's no band, then there's one. There's a band here at a different frequency. That one's similar. And then these are sharp. And then these two are sharp, you know. So the fingerprint region looks different, but the group frequency region looks similar, right? So who in the group today is a forensic science person? I think, what, Connie, were you forensics or are you chemistry? No, you're chemistry, aren't you?
Can you repeat that?
Connie, you're a chemist, right? You're not a forensic science person, right?
No, I'm a chemist.
Yeah. I was wondering if anybody here was forensic science. Ah, Brenda. Ah, excellent, Brenda. So basically, this is where the forensicist has to keep himself. And Tyler, excellent, great. Oh, Tyler, you're also forensics. Cool. So the forensicist has to not invoke a lot of interpretation or a lot of controversial stuff, right? So what the forensicist will generally do is they'll match things, right? So if you have an unknown fiber, you take an infrared spectrum of a fiber, like you find a fiber at a crime scene, right? You can use a infrared spectrometer with a microscope with a microscope attached. You can get a spectrum of that fiber, right? So that alone is never used. Say, oh, this is a hair from a beagle or whatever. You never say that. Right? What you do, and let's say it's a, I don't know, from a carpet or something, right? What you would do is you would take fibers from a bunch of similar carpets and then, or from similar carpets and from hair and other similar fibers, right? And you put them side by side and you take the infrared spectrum of each one, right? And you see which one matches your unknown, right? And that's a completely qualitative match, right? You never try to explain, I mean, in general, you don't try to explain the individual structures. You just say, well, here's a hair, here's a carpet fiber from, Best Buy, here's a carpet fiber from, Home Depot, here's a carpet fiber from, this wool carpet or whatever, and then you just match them up until you find a match. Right? When you find a match, you can say, okay, there's a low probability that that match comes from something random, right? If you can show that the other comparable fibers don't match, right? And that's the type of thing that our forensic scientists will do, in my experience, my limited experience there. And in that case, the fingerprint region, actually, all these regions would be important, So you would just try to match the entire spectrum. And you'd put it alongside other guys. Cool. So let's see here. Now, another thing you can do is you can use you can mix your analyte with KBR, right? This is, and then you just reflect the infrared beam into it and then collect all the radiation that's coming out and feed it into the detector, right? And that's called diffuse reflection. And in diffuse reflection, you've got an incident beam here. And then you've got a bunch of scattered beams. And you do your best to collect a wide angle of scattering, right? So you focus the beam onto the sample, then you collect the radiation that comes off and you do your best to focus that onto a detector, right? And the diffuse reflection, right? It's not exactly quantitative in terms of the relative reflectance, the diffuse reflection for a sample divided by a blank, say a similar particle size blank. But if you take this value, this reflectivity, and you transform it like this, take 1 minus that over 2 times that, that will equal K over S, right? And K has this concentration in it. So you can compare standards like this, right? It's basically saying this Kubelka monk, this parameter, this thing here is called a Kubelka monk. Is proportional to concentration. Now, it's not always used, right? Because IR is more often used for qualitative analysis. But you can see here's a diffuse reflection spectrum of caffeine taken in the infrared. And there's the spectrum before and after Kubelka-Monk transformation, right? And it just cleans up the baseline a little bit, It doesn't change it so much. Makes these peaks more intense, makes the, it sort of emphasizes certain peaks there, right? And lastly, but not least, I'd like to talk about an ATR spectrum, what an ATR spectrum is. Well, and I'm rushing here, I'm sorry. I want to finish this today. I'm taking too much time. But an ATR, or attenuated total reflection, takes advantage of the phenomenon of total reflection to get a spectrum. Right? And basically ATR means that you use a waveguide which is typically a slab of material that with a high refractive index N1, right? And you take advantage of Snell's law here, right? And what this means is that N1 sine theta 1 will always equal N2 sine theta 2, right? But at a certain point, this angle here, theta 2, theta 2 will be greater than or equal to 90 degrees, right? And then its sine value will be 1, and then the theta 1 then will be equal to the arc sine of those ratios. It doesn't really matter here what the exact value is for our purposes. But if you use N2 of 1 and N1 of 1.5, for example, you get 40 degrees. So this guy might be 40 degrees. And then, so in this case, this angle here will also be 40 degrees, right? It's like, that's just, angle of incidence equals angle of reflection. Just that there's no transmitted beam out here, right? But at this interface, at this N1, N2 interface, where this total internal reflection is taking place, there is some electric field strength from this radiation that leaks out into this rare medium out here, right? And so there's a region of space here where the electric field is evanescent. And evanescent means vanishing, right? And it starts intense right at the surface, and then it gets weaker, right? And what happens is that in this evanescent region, molecules that absorb this frequency of light can reduce the intensity of the reflection without actually steering the beam out of the across the interface, right? But absorption can take place here. Right? And this is actually, of all the techniques that we've discussed so far, this method, I'll just let you guys read that on at your own convenience. This method is probably the most popular infrared sampling method nowadays. And you just take the negative log of the reflectivity, and that can give you an absorbance value for anything sitting on top of the crystal here. And N2, this would be your sample here. And N1 is going to be zinc selenide or diamond. These are the two materials that are most commonly used there. And basically all you need to do is you need to use a beveled edge to couple the light in, and then to couple the light back out. So, and then you can get a spectrum of anything you put on top of here with an effective path length of it's like lambda over 4 or something like that. So it comes out to be about, maybe 2 microns or so. All right, guys. So that's all for today. And evanescence makes me wake up. Cool. So I'm going to have, we're going to do one more lab. It'll be an easy one. It's fluorescence. There's data on Canvas. And I'm going to record today's lab starting at 10 o'clock. So I'll put out a Zoom invitation for 10 o'clock. Anybody who wants to join me at 10 o'clock is welcome to do so. And if it comes out good, I'll put this lab out. I'm going to put it out to everybody anyways. Hopefully it'll be good. So any last questions?
Dr. Terrell, did you get my email?
I got your text, yes.
No, my email.
I don't know. I haven't been checking my email. I've been giving lecture.
I sent you my lab.
Okay, that's good. Is there any way you could turn it into Canvas or?
Well, because it has the Excel files too. It has more than one file.
Oh, you can put them. You can put them both up there. I get them both.
You get them both? I don't know how to do that, and it's too complex. I'm tired. It was too early in the morning. Okay.
All right. Well, just when you get a chance, upload them both to Canvas. That's much easier for me to keep track of stuff.
Okay.
If you don't, I'll get over it. But and I'll still get you your grade most likely, but you may have to bother me a little bit. So I'll see everybody at lab. Everybody who wants to come. All right. Bye.
Bye, Dr.
Bye. Thank you guys.
Bye, Dr. Terrell.
Bye. Bye. Thanks everybody.